Picture yourself as an archaeologist of the cosmos, carefully unlocking a time capsule sealed not for centuries, but for more than 13 billion years. What extraordinary stories might spill out about the birth of everything? What would you learn about the moment when the very first stars flickered to life, transforming a featureless void into the universe we now inhabit? This is not just a thought experiment. Thanks to a series of astonishing technological feats, scientists are now peeling back the deepest layers of cosmic history, revealing secrets once thought forever out of reach. For decades, astronomy has been a relentless race against the limits of human ingenuity. Every leap in our understanding of the universe has been powered by new tools and sharper eyes. When the cosmic microwave background, often called the afterglow of the Big Bang, was discovered in the mid-1960s, it provided a stunning snapshot of the universe just 380,000 years after its fiery beginning. Imagine, a universe so young that galaxies did not yet exist, and stars had not yet ignited. The entire cosmos was a hot, opaque fog of charged particles with light itself trapped in a cosmic prison. Only as the universe expanded and cooled did this fog lift, allowing photons to finally roam free. This ancient light, stretched into microwaves over the eons, fills the universe even today. It is a living fossil, carrying clues about the earliest moments of existence. Yet, as profound as the discovery of the cosmic microwave background was, it was only the beginning. The real treasures, those faintest signals from the very first stars, remained hidden, buried beneath layers of cosmic noise and the interference of our own bustling planet. The challenge was immense. Space-based telescopes such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite provided our first tantalizing glimpses into this epoch, mapping subtle temperature and polarization patterns across the sky. These missions revealed that the cosmic microwave background is not perfectly uniform. Instead, it contains minute fluctuations, ripples that would eventually seed the formation of galaxies, stars, and planets. But these orbital pioneers faced their own limitations. Instruments in space cannot be easily serviced or upgraded, and their sensitivity is ultimately capped by the technology available at launch. Back on Earth, astronomers faced an even more daunting obstacle. Our planet's atmosphere is a noisy, turbulent sea of electromagnetic waves. Detecting the faint microwaves from the dawn of the universe is like trying to hear a whisper across a crowded stadium. For decades, the consensus was clear. Ground-based telescopes would never be able to pick up the polarized light left behind by the first stars. As Professor Tobias Marriage, the leader of the CLASS project at Johns Hopkins University, put it, microwave signals from the cosmic dawn are famously difficult to measure. Overcoming those obstacles makes this measurement a significant achievement. But science thrives on defying assumptions. Enter the cosmology large angular scale. Surveyor, known as CLASS. This pioneering telescope is perched high in the Atacama Desert of northern Chile, at an altitude of nearly 17,000 feet, higher than many mountain peaks. The location is no accident. The Atacama is one of the driest places on Earth, with a sky so clear that it is often likened to being on another planet. This arid, high-altitude setting dramatically reduces atmospheric interference, providing CLASS with a unique vantage point from which to scan the heavens. Since first capturing light in the year 2016, CLASS has methodically mapped more than 3/4 of the night sky. Its instruments are finely tuned to multiple microwave frequencies, specifically in the 30 to 40, 90, and 150 gigahertz bands. By observing at these different frequencies, the telescope can expertly distinguish between signals from our own galaxy, such as emissions from interstellar dust, and the ancient whispers from the cosmic microwave background. This technological sophistication allows CLASS to tease out the elusive polarized signature left by the universe's first stars, a feat once deemed impossible from the ground. What exactly did CLASS find? By meticulously comparing its data with those from Planck and the Wilkinson probe, the team detected the faint, polarized imprint on the cosmic microwave background caused by the first generation of stars. These primordial giants, formed when the universe was less than 1 billion years old, unleashed torrents of ultraviolet light that rayonized the hydrogen fog left over from the Big Bang. This rayonization process separated electrons from atoms, allowing them to scatter cosmic microwave background photons in a way that left a distinctive polarization pattern, a kind of cosmic fingerprint. But every answer unlocks new questions. If ground-based telescopes like CLASS can now peer into the cosmic dawn, what other secrets might be within our grasp? Could we soon detect the signature of primordial gravitational waves, ripples in space-time generated during the universe's earliest instance? Such a discovery would not just rewrite textbooks. It could open a direct window onto the physics of inflation, the process that set the stage for everything we see today. As more data pours in, the landscape of early universe research is changing at breathtaking speed. CLASS is only the first step in a new era of precision cosmology. The Simons Observatory, now under construction in the Chilean Andes, promises to revolutionize our view of the microwave sky. With its 60,000 detectors, the Simons Observatory will achieve unprecedented sensitivity, mapping the cosmic microwave background with a resolution and accuracy never before possible. Projects like CMBS-4 aim to go even further, targeting a sensitivity of delta T over T of approximately 1 microkelvin per arc minute and an angular resolution finer than 5 arc minutes. These advancements will allow scientists to probe the universe's infancy with a clarity once reserved for dreams. Meanwhile, complementary experiments such as the Atacama Cosmology Telescope, which has achieved a resolution of 1.4 arc minutes, and the EDGES experiment, which detected a 21-centimeter absorption profile centered at 78 megahertz, are providing independent confirmations and new perspectives. The upcoming square-kilometer array will explore the cosmic dawn by studying neutral hydrogen across the universe, offering a completely different window into galaxy formation and the end of the cosmic dark ages. What makes all this possible? Behind the scenes, a marriage of cutting-edge detector technology, advanced data analysis algorithms, and international collaboration is driving progress. The sensitive receivers used by CLASS were inspired, in part, by research into mobile phone antennas. Algorithms originally designed to filter out faint microwave signals now optimize everything from medical imaging to environmental monitoring and telecommunications. This is a powerful reminder. Investments in fundamental science often yield practical benefits that ripple across society, driving innovation in ways no one can fully anticipate. The impact of these discoveries extends far beyond the laboratory. As astronomers refine their measurements, the standard model of cosmology, the framework that describes the origin and evolution of the universe, is coming under increasing scrutiny. Surprising findings, such as the discovery of galaxies existing only 300 million years after the Big Bang, are forcing scientists to rethink the timeline of reionization and the properties of early galaxies. Dr. Joris Wittstock from the University of Copenhagen puts it this way: the discovery of a galaxy existing only 300 million years after the Big Bang challenges existing models of reionization. Other experts echo this sense of excitement and upheaval. Professor Michelle Trenti from the University of Melbourne notes, the unexpected Lyman alpha emission in early galaxies suggests that these objects may have unique properties. In other words, the first galaxies might have been more efficient at producing and releasing ionizing radiation than previously thought, altering our theories about how quickly the universe was transformed from darkness to light. As more advanced telescopes come online, we may even detect the telltale polarization patterns of primordial gravitational waves, signals predicted by inflationary theory but never yet observed. Dr. Suzanne Staggs of Princeton University reflects on the stakes. The high-resolution measurement opened the window to a time when the first cosmic structures were starting to assemble. But what does this all mean for life here on Earth? The answers are both practical and philosophical. On one hand, the technology developed for cosmological research is already improving lives, whether by enhancing satellite communications, advancing medical diagnostics, or contributing to climate science. On the other, these discoveries challenge us to reconsider our place in the universe. The fact that we can detect signals from the dawn of time is a testament to human curiosity and collaboration, a reminder that our species is hardwired to explore, question, and dream. There is also an economic dimension. The pursuit of ever more sensitive measurements drives progress in cryogenics, electronics, and data science. Companies that build superconducting detectors for telescopes often spin off innovations used in industry, from precision sensors in manufacturing to advanced imaging in hospitals. The global push to map the cosmos is, in a very real sense, an engine of economic growth and technological advancement. For those watching from home, the story of CLASS and its successors is a lesson in perseverance, innovation, and the power of bold ideas. When scientists dare to challenge conventional wisdom, when they build telescopes on remote mountaintops or design detectors that operate at a fraction of a degree above absolute zero, they open doors not just for astronomy, but for all fields that build on new knowledge. This is how transformative change happens, by investing in curiosity, supporting basic research, and taking risks that others deem too great. Looking ahead, the next decade may bring answers to some of cosmology's most profound questions. Will we find the smoking gun of primordial gravitational waves? Will new data force us to revise our understanding of dark matter, dark energy, or even the very laws of physics? Already the boundaries of possibility are shifting. As Dr. Erminia Calabrese of Cardiff University observes, the circle continues to close around our standard model of cosmology, with these latest results weighing in strongly on what universes are no longer possible. And here is a little-known fact. The very technology that now allows us to listen to the whispers from the dawn of time owes its existence to advances made in everyday mobile phone research. Sometimes the most profound breakthroughs are fueled by the most ordinary innovations, a new antenna here, a better algorithm there. In the end, the universe rewards those who are curious. As today's telescopes decode signals sent billions of years ago, we are reminded that tomorrow's breakthroughs may come from the most unexpected directions. Perhaps you, watching this now, will be inspired to join this grand adventure, to push the limits of what humanity can know, to build the next generation of instruments, or to ask the questions no one has thought to ask. If you are moved by the relentless human quest for answers, if you want to witness the secrets of the cosmos revealed one discovery at a time, then subscribe and join us on this extraordinary journey. The universe has only just begun to reveal its